Welcome back to the deep dive. Today we're getting into something really fundamental, the wrap-up of Work and Potential Energy from Feynman's Lectures, Vol.1. Seriously, if you want the concepts that connect basic mechanics to, well, almost everything else in physics, this is where it's at. We're not just summarizing. We want to really get that Feynman intuition, that elegance he brings.
Absolutely. This chapter is like the keystone. It pulls together work, energy, how paths matter or sometimes don't matter, and then lands on this beautiful idea of fields. It's kind of the ultimate shortcut to seeing how these ideas unify.
Okay, so let's jump right in with maybe the trickiest bit first, defining physical work.
It's not the everyday meaning, is it? It's that specific formula, $1 int, math, BFS, CD, A side, D best, BFS line.
Right, and that integral, that dot product,
Mhm.
it basically means you need a force and you need movement, displacement, and critically, some part of that force has to be pointing the same direction as the movement.
If there's no movement or if the force is totally perpendicular, then zero work.
Exactly, zero physical work. Which brings us to that classic example Feynman uses, holding a really heavy weight. You're straining, muscles burning, using up energy like mad.
Oh yeah, physiologically you're working hard, no question. Your muscles are contracting, using ATP, generating heat.
But from a physics perspective, on the box itself, since that displacement, nath-BF-SS is zero.
No work is done on the box. It sounds weird, but that distinction is absolutely key. Physics work is about force causing motion of the object itself, not about, say, the chemical energy inside your arm.
Huh.
It sets a really rigorous foundation.
Okay, got it. So let's take that definition and see how it applies when things are forced to move along specific paths. Segment 1. Work, constraints, and kinetic energy.
Right, constraints. Think about a bead sliding on a wire, or maybe a train car on a track. The object isn't free to move anywhere, it's constrained.
And the wire or the track pushes back, right. There's a force involved in keeping it on the path, a normal force, maybe tension.
Exactly. Those are the constraint forces. Now, you might think, okay, to find the total work, I need to calculate the work done by gravity, maybe friction, and this complicated constraint force.
Which could be changing direction all the time as the track curves. Seems messy.
But here's the elegant part. Go back to our definition. That constraint, force, the push from the track, the pull from a string in simple cases, is almost always perpendicular to the direction the object is actually moving at that instant.
Oh, right. A normal force is normal, perpendicular to the surface.
Precisely. So if the force vector math BFS constraint is perpendicular to the tiny displacement vector math BFS at every point,
Then the dot product, math BFS is zero. The constraint force does no work.
bingo. That's the core idea from section 14-2. Constraint forces typically do zero work, and that is a huge simplification.
So when we use the work energy theorem that the total work equals the change in kinetic energy,
We only need to worry about the work done by the other forces, the active forces like gravity or someone pushing it or a spring. We can often just ignore the work done by the constraints, keeping it on the path.
that makes things way easier. It connects the change in the object's speed, its kinetic energy, directly to the work done by the forces that are actually trying to speed it up or slow it down.
Exactly. It's a fundamental link.
Okay, that's a big simplification. But now segment 2 introduces an even more powerful idea, I think. These special forces, where the calculation becomes incredibly simple because the path doesn't even matter. Conservative forces.
Yes, this is where it gets really elegant.
Yeah.
A force is called conservative if the work it does moving something from point A to point B depends only on the start point A and the end point B.
Not on the wiggly path you took in between.
Nope. Doesn't matter if you go straight up or take the scenic route. If the force is conservative, like gravity, the work done by that force is exactly the same.
That still feels a bit strange. If I carry a heavy bag up a long flight of winding stairs, it feels like way more effort than taking the elevator straight up.
But remember the physics definition of work. When you walk horizontally along a stair landing, gravity is pointing down, your displacement is sideways. The work done by gravity during that horizontal part is zero.
Okay. Gravity only does work when you change your vertical height.
Exactly. And because of this path independence, we can define something incredibly useful. A potential energy function, usually written as τ.
This is the big shortcut, right? Instead of calculating the work integral along some path.
You just find the difference in the potential energy value between the start and end points. The work done by the conservative force going from 1 to 2 is simply W1 to 2 your 1 day. Notice the order. Initial minus final potential energy.
And if only conservative forces are doing work on our object.
Then the total work done is 0,1. delta U of 1, the negative change of potential energy. But we already know from the work energy theorem that the total work is also equal to the change in kinetic energy, delta W.
So, delta T interval is delta U, or rearranging delta T plus delta U equals $1.
Which means the change in the total mechanical energy, T plus U, is zero. In other words, T plus U remains constant. That's the principle of conservation of mechanical energy.
Kinetic plus potential energy stays the same. That's huge. It means we don't need to know how it got from A to B, just the energy states at the beginning and the end.
Precisely. It bypasses all the messy details of the motion itself. Feynman gives those key examples. Near Earth, gravitational potential energy is $1 mgz2.
Right, depends only on height.
For an ideal spring, it's $1 fran2 k-2, depending only on the stretch or compression, $6.
Makes sense.
And for gravity between, say, the Earth and a satellite, it's $1 nis gms teroni, depending only on the distance for dollars between their centers.
Let's take that last one, the general gravity case. You mentioned using this for escape velocity.
Yeah, it's a classic calculation that shows the power of energy conservation. Suppose you want to launch a rocket straight up from Earth's surface, radius in, so that it just barely escapes Earth's gravity, meaning it reaches infinitely far away with essentially zero speed.
Okay, so initial state at 21, speed $5, final state at 150, speed $1.
Right, so initial energy is $2 plus UI is Tor 12 milliv2 GMA.
And the final energy, way out at infinity, speed is 0, so $2F, and potential energy phi the OFE10 or GM at LaVithi, which is also 0.
So TF plus US is 2, so final. Since energy is conserved, we set initial equal to final. Strac 1, 2 milliv2 GMA consorted with Zeller.
And solving for $5, you get 2 body hours. T equal is 2 GML. That's the square of the escape velocity.
Right.
We don't have to integrate the force over the path or anything.
Exactly. Just compare the energy at the beginning and the end. It's incredibly efficient.
But okay, real life intrudes. Section 14.4 brings up the unavoidable issue, friction. If I slide a book across the table, it slows down and stops. Kinetic energy is clearly lost.
Right.
What happens to T plus U? Well, text constant then.
Yeah, friction is the classic example of a non-conservative force. The work done by friction definitely depends on the path. Slide the book further. Friction does more negative work. Mechanical energy, T plus U, is not conserved when friction is involved. It seems to just disappear.
So is energy conservation wrong?
Not at all. This is where Feynman makes a really deep point. The fundamental forces we know, gravity, electromagnetism, seem to be perfectly conservative. Forces like friction and air resistance are usually macroscopic, kind of statistical effects arising from those fundamental interactions.
Okay, so if the mechanical energy isn't conserved, where does it actually go?
It turns into internal energy, heat, basically. When the book slides, the surfaces rub.
Yeah.
The atoms at the interface start jiggling and vibrating much more vigorously.
Ah, so it's like the kinetic energy of the whole book gets transferred into the microscopic kinetic energy of its atoms and the table's atoms.
Exactly. And maybe some potential energy stored in the bonds between atoms, too. The point is, the energy isn't lost. It's just transformed into a less organized internal form.
So the statement T plus U, text constant, is only for mechanical energy.
Right. But if you define your system properly, including the book, the table, the air, everything, and account for all forms of energy, kinetic, potential, and internal energy, then the total energy of that isolated system is conserved. Always.
That's a crucial clarification. The law holds we just needed a broader definition of energy.
Precisely. The apparent loss is just a transformation.
Okay, let's move to the final piece, maybe the most mathematically satisfying part. Section 14.5, potentials and the idea of fields.
Right. This kind of ties it all together. We've seen that for conservative forces, we can define this scalar quantity, potential energy $E, which depends only on position 6x, y, z.
Just a single number at each point in space.
Yes, a scalar field. Now, the amazing thing is, if you know this scalar field ux, y, z everywhere, you can figure out the vector force math BFPF at any point.
How do you get a vector with direction from just a scalar, a number?
Through the concept of the gradient. The force is the negative gradient of the potential energy.
Okay, nobla, the gradient. What does that mean intuitively?
Think of the potential energy dollars as creating a sort of landscape, like hills and valleys. The gradient nobla u at any point is a vector that points in the direction of the steepest uphill slope, and its magnitude tells you how steep that slope is.
Okay, uphill. But the force is negative gradient.
Exactly. So the force vector math BFF points in the direction of the steepest downhill slope. It tells the particle which way to roll to decrease its potential energy the fastest.
Like a ball rolling down a hill. The force of gravity pulls it along the steepest downward path. That makes intuitive sense.
It's a beautiful connection. And mathematically, it's precise. The x component of the force, fifth act, is just the negative rate of change of $2 as you move purely in the x direction. Fifth x, partial u, partial x, same for 5 times and 5 times.
So knowing how the potential changes in each direction tells you the force components in those directions?
Yes. You get the full vector force field from a single scalar potential field. It's incredibly economical.
And this isn't just for mechanics, right? Feynman draws the parallel to electricity.
Absolutely vital. It's the exact same mathematical structure.
Huh.
In electricity, instead of potential energy, due dollar, we often talk about the electric potential, E of I, which is potential energy per unit charge.
So $1 equals a 5 for a charged dollar.
Correct. And the electric field, math BFE, which is the force per unit charge, is given by the negative gradient of the electric potential, math BFE F WFE.
Wow. So gravity and electricity use the same fundamental mathematical relationship between a scalar potential field and a vector force, or force-like field.
It's a deep pattern in nature. The example of the parallel plate capacitor illustrates it well. If you have a constant electric field, math BFE, between the plates,
Then the potential dialer must change linearly with position, right? Because math BFE is the negative derivative gradient of phi. Constant derivative means linear function.
exactly. And knowing that simple linear potential function immediately tells you the work needed to move a charge, the field strength, everything. It's all encoded in that scalar potential.
Okay, let's try to quickly recap this journey through the chapter. We started by really nailing down the physics definition of work force times displacement in the same direction.
Right, distinguishing it from just effort. And we saw how constraint forces often do zero work, which simplifies calculations.
Then we hit the crucial idea of conservative forces, where work is path independent, letting us define potential energy $2.
Which immediately led to the conservation of mechanical energy, T plus U, text constant, a super powerful tool for solving problems by just looking at the start and end states.
We address non-conservative forces like friction, seeing they don't break energy conservation overall, but just transform mechanical energy into internal energy.
The total energy is always conserved if you account for everything.
And finally, we reached the mathematical peak, describing conservative forces using a scalar potential field due no, where the force in math BFS is simply the negative gradient, nobly UA.
A structure that elegantly reappears in electromagnetism with the electric potential needle of fish and electric field math fish. It shows this profound unity.
It really does. The elegance of describing complex vector forces with a single, simpler scalar field is striking. So here's something to ponder. If nature so often describes forces as pointing down the slope of some potential landscape, what does that suggest about stability and where things tend to end up?
Well, it suggests things naturally seek out the valleys, the points of minimum potential energy. That's fundamentally where equilibrium lies.
Always rolling downhill, seeking the lowest point. A perfect place to leave it. Thanks for joining us on this deep dive.